So to finish off the course, we have applications for logarithmic and exponential equations, although really the applications are all exponential equations. What we have first up is money. If we think about interest, a simple applied interest takes the equation I equal PRT, where P is the principal, the amount you start with, R is the rate or the interest rate, and T is the period or the number of times the interest is applied. So we're going to call this number of pay periods. So something to note is that simple interest only applies interest to the original base amount. We're not going to do anything with simple interest because we want to talk about compounding interest. So in compounding interest, the interest rate is applied to the current value as opposed to the original value. I'm going to say reapplied for every pay period on the current value. So what that would look like is, well, we'll say we have 1 month, then we have, well, this is going to be P times 1 plus the rate. So the 1 there is for the original amount, because if you distribute the P here, you'll have P plus PR. So you have the original principal amount plus the interest applied to the principal amount. If I take it another month, say 2 months, then I have P times 1 plus R, and it's times 1 plus R again. So as opposed to simple interest, where I would just make T equal to 2 if I wanted the interest, compound interest, I find the amount I end up with after applying interest after each month. This is weird. That's S. There we go. So this is the current amount before we started the second month, and then at the end of the second month we apply the interest again. So the new amount is going to be 1 plus R times the amount we started with, and this proceeds forever. So we have two compounding interest formulas. We have standard, and this does follow my little mini example before. It's just that we're going to be fixing one of the variables t to be in years when we set this up. So the amount after t years is going to be equal to P, the principal, times, and we have 1 plus R over N, raised to the power of nt. So n is the number of payments per year. In my previous example, I would have had it set up so that I use t in months, and then the number of payments per month is 1. And this would build up p times 1 plus r to the n. But the standard is to use years, because typically loans and savings accounts and other things that build interest are looked at over the course of years. You have a 30-year mortgage, you're not going to have a 5-month mortgage. So R is the rate, and T is the number of years. So for example, if I have $1,000 invested, at an annual rate of, let's see, 10% compounded, we'll have a couple of options. Annually, and monthly. We'll just look at 2. Actually, let's have fun. We'll also look at the daily. I'm not going to do this with a calculator, but what would precede for these problems is a calculator. If I have $1,000 invested at an annual rate of 10%, we'll start with the annually, then my amount function will be A equal to 1,000 times 1 plus, if I'm doing it annually, that's once per year, so I just do the rate, 10%, which is 0.1 divided by 1 raised to the power of 1 times t. If I set it up monthly, then A of t is equal to 1,000 times 1 plus 0.1 for the interest rate. And there are 12 months in a year, and this is going to be raised to the power of 12t. And then daily, we'll have A of t equal to 1,000 times 1 plus 0.1 divided by 365 raised to the 365t. So if you've got a calculator handy, you can compare all 3 of these by looking at how much do you get after just 1 year. Let's see, A of 1, my $1,000 should grow to 1,100, which makes sense because 10% of 1,000 is 100, and if I just apply the interest once, then I'm only going to gain $100. On the other hand, if I do this monthly, I actually get a little bit more. If I plug in A of 1 into this version, I will get 1102.50. And the reason for this is it's going to compound a little bit after the first month, a little bit more based on the previous month, on the next month, and so it just builds up slightly faster. And if I do it daily, here we go, we get even more. We have 1105.16. Now, something you might recognize as a part of this gives us our continuous compounding variety. Because if I wanted, I could set it up to compound every minute. and there's a lot of minutes in a year. I'm not sure what they would do for leap years, but let's just ignore it. If I do continuous compounding, let's look at the parts that were changing in my regular compounding interest. It seems like only this part, the 1 plus r over n to the nt, is what was modified, because that's the part with the n, and the n is changing for the number of compounds per year. So if we let n go to infinity, you might remember this from a previous video, there's a limit in calculus. So the limit as n goes to infinity of 1 plus 1 over n to the nt, this is equal to e. Well, it just works out that if I have an r in there, limit n goes to infinity, 1 plus r over n to the nt, this will be equal to e to the r. So my continuous compounding formula will look like a of t equal to, we start with p, 1, nope, we don't need 1 anymore, because when we let it go to infinity, it turns into e to the r, and I forgot my t here on this part, rt. So I end up with p e to the rt. And let's see, how much money would we get if, with our example here, we would have, oh, let me change here. A of t would be equal to 1,000, using our previous example. E to the rate was 10%, so 0.1 to the t. And if I plug that in for 1 year, I get a of 1 equal to 1105.17. So barely better than 365. But this is the limit as I let the compounds go to infinity. So if I let it run compounding for every minute, I'd probably get exactly the same answer here in terms of dollars and cents. There are some other formulas in this section regarding the money, section 5.7, depending on what you're looking for, such as an effective rate of interest, meaning if I'm compounding monthly, what is my actual interest rate that I gain per year? It's actually slightly higher than, in this case, slightly higher than 10%. Let me scroll up. My effective interest rate would be 10.25%, because that's how much I gained over the course of 1 year with my monthly interest rate. There's also, you can find present value formulas, which give you, they say present value, but they actually give you the principal. So I guess they're trying to speak of the equations in the sense that what will the future look like. But we're not really in the kind of class to overly concerned with additional formulas here. It's enough to look at the continuous compounding formula here, because that's what springs us into the rest. Is if I'm looking at continuous compounding, this is continuous growth. And natural growth happens continuously, essentially. So our governing equation for almost all natural situations of unlimited, we'll say, growth or decay, these will all follow the master formula we'll say A equal to A0, say A of t, make it a function, e to the kt or rt, whatever letter you want to use. We actually get these as a result of the solution to a differential equation. The question posed is, what kind of function has a growth rate that is proportional to its current size or population? Which makes sense for natural growth, because the bigger a population is, the faster it's going to grow. But a lot of the questions that we're going to be having, we're not going to know what this k value is. We'll only know what the initial value is. So first up, we'll talk about radioactive decay. Next, as an example, we can talk about carbon dating. Let's see, carbon-14 takes how long? 5,730 years to decay to half its value, or amount, I should say. This is called the half-life here. So in our setup, we have some artifact or some material. We'll say it contains approximately, oops, that's weird. Where did that come from? Let's see, what do we got here? 1.67% of the original or appropriate value. And I'm just going to call this C14. So the question we have here is, when was it made? And we have all the information we need right here, actually. We start with our master equation. Let's see, what should we call this? Well, we'll just call it A0 e to the kt. Now what we need is, we need to have the k. I know that after 5,730 years, we're going to get half. So we don't actually need to know the initial amount here. We know that, oops, A of 5,730 is equal to 1/2 of A0. That A0 is the initial amount. But this is also equal to, with the function, A sub 0 e to the k times 5,730. And then what happens pretty much all the time with these problems is the initial amount always cancels. So it's not important that we know what the initial amount actually was. But I do have the exponential equation. Let me get rid of that. 1/2 equal to e to the 5,730 k. And we need to solve for k. So we'll do that. Let's see, what should be natural log of both sides. Natural log of 1/2 equals, a natural log would cancel with the e, giving me 5,730k. So k equals ln 1/2 over 5,730. Now what this says is the rate constant, k up there, is going to be whatever that number is. And that's what I need in order to solve my problem. And in fact, every problem practically in section 5.8 is going to follow the same kind of set of steps. You start with a blank equation, you fill in what you know, and then you try to solve for the k. Or maybe you're given the k and you need to solve for the time. Sometimes you'll start with the time and you need to find the k. Sometimes you'll start with the k and you'll need to find the time. Depends on the question that's being asked. You should always just start with your equation, and then if necessary find your k, and then you go back to the question and see what they're actually looking for. In this case, we wanted to know how much time it took. So we're trying to solve an equation that looks like a of t equals 1.67%. So this is 0.0167 of some initial amount that we don't know. But when I fill in the formula, or the equation, I'll get a sub 0 e to the lovely number ln of 1/2 over 5,730 times t. And the a zeros cancel, and I'm trying to solve for t again. But the steps are the same here. I take natural log of both sides, so I've got natural log of 0.0167 equals, the natural log will cancel with the e, so I always have kt as a step here. And then I just solve for t. And the answers for these problems are always going to be gross. We can't go further than this without the aid of a calculator. Now, the population growth ones work pretty much exactly the same way. The only difference between growth and decay, growth has positive k values, but this decay problem has a negative k value. Decay has negative k values. And if you check a graph of natural log, or any log for that matter, log of 1 is equal to 0, doesn't matter what base you are. So if I plug in numbers that are bigger than 1 into my logarithm, I'm going to get positive numbers. But if I plug in numbers between 0 and 1 into my logarithm, I always get negative numbers. So that's what tells me that this k is going to be a negative value. And a negative in the exponent is going to tell me that my values are going to be shrinking, which makes sense for decay. If I had a population growth problem, all this work would be exactly the same. It's just my k value that I end up with would be a positive number. So skipping population growth, we're going to do a special growth and decay type of problem called Newton's law of cooling. This actually works exactly the same way, but we have to be very careful with the Newton's law of cooling ones. Let's see, for the regular growth and decay, the growth or decay is proportional to the population. Now, Newton's law of cooling, the difference in temperature between an object and its environment is proportional to the rate of change of the object, rate of change of the temperature of the object and its environment. So what that's saying is I've got a of t equal to a0 e to the kt, but a0 equals, and then you can set this up to go either direction. The books like to separate them and say, no, you can only do it in the right order, but that's false. A0 is T A minus T. So TA is ambient temperature or environment. Think of this as the temperature of your freezer. And then the T is the temperature of the object. So the can of Coke you're not supposed to put into the freezer. Let's see. I should have put a 0 here and a 0 here, and this is the initial. Capital T is still going to be our variable. So A of T is equal to TA minus T. Now, the assumption is that the ambient temperature doesn't change. It's constant, or it's a large enough body of heat that the temperature of the object does not affect the system. So let's set this up. An object is heated to 100 degrees. Pick your scale. Let's go ahead and say Celsius because that's more extreme heat. And then allowed to cool in a room at a room of 30 degrees Celsius. Now, what actually happens in real life is if you put a hot object in a room, then the room will actually start to feel warmer. But the temperature of the increase in temperature of the room is usually minuscule compared to the decrease of the temperature of the hot object. I face this issue frequently with, say, a computer. A computer processor can regularly reach, nearly 100 degrees Celsius, but the heat removal system that you have for your computer, maybe you've got a radiator, maybe it's just a fan that's blowing, or if it's a small enough processor, maybe it's just a simple heat sink, but it is dispersing heat out into the air. But if you have it running long enough, then the room will start to feel really warm. Now the problem with these temperature ones is we always have to have some other kind of a scenario. Before we continue with this, we should actually say here, the initial temperature of the object is 100, and the temperature of the room, the ambient, is 30. So A0 for my formula is going to be 30 minus 100, which is equal to minus 70. It's called Newton's law of cooling, but I can also use Newton's law of heating. The direction of this difference here just determines whether your exponent will be positive or negative. It doesn't matter nearly as much as some of the books would lead you to believe. But let's continue. So we have some information. If the temperature of the object is 80 degrees after 5 minutes, then we want to know how long until it's cooled to 50 degrees. Oh, come on. So let's see what our goal actually is here. We know the temperature of the object is 80 degrees after 5 minutes. So A of 5 minutes is equal to, always remember to subtract it from the temperature of the room. So we have 30 minus 80, which is minus 50. But A of 5 is equal to, our initial there is minus 70 times e to the k times 5. And I pulled that just from the blue up there. So what we're missing is the k. Because I won't be able to answer this question, I won't be able to solve for the time when I get 50 degrees for the object until I have the k. So we'll set these equal to each other. We've got minus 50 equals minus 70 plus e to the k times 5. So we end up with 50 over 70 equals e to the 5k. Natural log both sides. Natural log of 50 over 70 is equal to 5k. So we know my k is equal to the natural log of this number. Actually, I can simplify that to just 5 over 7 all over 5. Okay, I have my k. So my actual full equation is a of t equals a0, which was minus 70, e to the k, natural log of 5 over 7 all over 5 times t. Now we can answer the question, how long until the object cools to a temperature of 50 degrees? So we're trying to solve a of t equal to 50 degrees. So you need 30 minus 50, which is equal to minus 20. Right, that's the number we want to plug in there. So we need minus 20 equal to minus 70 e to the kt, so natural log of 5 over 7 all over 5 times t. Now this is what I want to solve for t. But just like that previous problem, this is not going to be, we're not going to have any sense. Just like in the previous problem, we're not going to have any sense of the number we get without a calculator. So let's see what we'll have here. We'll have minus 20 over minus 70 equals e to the kt. Natural log of both sides, natural log of 2 over 7 equals the natural log will cancel with the e, so I get natural log of 5 over 7 over 5 times t, and we can just solve that for t. So we'll get t equal to natural log of 2 over 7 times 5 divided by natural log of 5 over 7. That's what we'll end up with. Now both of these natural logs will give me negative numbers, but the negatives will cancel, so I know that this is going to be a positive number, so my answer will make sense. And I should say this is in minutes. So let's see, what does that look like in minutes? This looks like about 18.6 minutes. That's all we need to do for the class. If you're interested in biology and realistic populations, there's a logistic model, but that's not a fun topic for pre-calculus as it is. The equation is in the book, but we won't need to talk about it. It's a better discussion in a differential equations class or a differential equations class that is designed for biology, or maybe a biology for calculus for biology. So this is the last video for the class and the last topic that can appear on the final exam.